And this is a three-dimensional plane which is similar to the triplan plane of a unit cubic system unit cell. This is 110 plane. Sorry, one triple one plane, not one plane. This is triple one plane, 111 plane of a unit cell. This is your oblique plane where our consideration or calculation will be made on. So, as we developed, as we know, the normal stress. Here we'll go for the normal stress and the shear stress on any oblique plane. What will calculate here? The normal stress and shear stress. We'll go for here the what is the value of the normal stress and the shear stress in any oblique plane. So as it is, as we are considering it is a principal plane. That means here the particular oblique plane, a principal plane in which there is no shear stresses. So we develop the equations for the normal and shear stresses on any oblique plane first. First, we have to develop the normal stress and the shear stress on any oblique plane. So, as we know, we have taken the direction cosines L, M, N. L is the between the stress. L is between the normal stress and just L is the angle between the normal stress and the x-axis. So this is cosine between x-axis. This is L is for x-axis, M is for y-axis cosine angle, and N for z-axis, the cosine angle between z and the normal stresses. So we can use the as here seeing this figure. This is our plane. The different axes, you know, this is our y-axis, this is our z-axis, and this is our x-axis. So these are the axes here. So who is talking? Neutral Rakesh Pradhan. So this is uh, the if you considering there is a total stress in the plane. Now consider the total stress is this is just useless. Total stress AC the now consider AC the total stress. Total stress on the oblique plane. We are considering this plane. I'm hatching this plane. We are considering this plane. We are considering this plane. This is the oblique plane. AC the total stress on this oblique plane. Now consider AC the total stress on this oblique plane. As we are considering, there is a stress, normal stress, and there is a shear stress. So relationship that we can easily build up here is that always we know that the shear stress, if it is our any case, if it is a normal stress, then shear stress will be perpendicular to it. So if it will be the total stress direction, now we can say this is sigma, this is tau, and this is total stress. Now we can develop a equation like that from the trigonometric relationship. C square is equal to sigma square plus tau square. This is one equation here. This is one equation here. Okay. Similarly, if we know that there are this is the total stress. Now we are considering this is the total stress. This is the total stress. This is total stress on the full body, this cubic body. This is the three-dimensional body. That means this total stress has three components in three axes. So we can say in x-axis, the total stress, the component of total stress is x-axis. In y-axis, that is sy, and in z-axis, it is sz. Are you clear it? The component of total stress in three axes is sx, this is Sx, component of total stress in x direction Sx, component of total stress in y direction Sy, and component of total stress on z direction Sz. So now we can develop, we can write another equation. We can say that simply. I'm just removing. I am just removing these lines. Don't think it is required now. So we can write that equation like in that manner also. S square is equal to sx square plus sy square plus sz square. Okay, you can write in that format also. So this is now equation 2. Now this is two equations. Now we have the two equations, and from initial we have developed, from the last class we are also developed the equations for Sx, Sy and Sz. In the last class we had already developed the equations of Sx, Sy and Sz also. What are these equations? What are these equations? Now I am going to delete this screen. It is better for you. No, so keep it. I will open another screen here, so it is better for you to see. A new screen is visible or last screen? We are seeing the last screen.
Sir, last screen, sir.
Last screen, na? New screen is visible to you?
Yes, sir.
Okay. So let's see, and we are already developed the equations of Sx, Sy and Sz. If you remember this, then will go better for us. So again, I am writing these equations. So equation for Sx is, as we have already proved there, that sigma x into L plus tau xy tau yx into m plus tau zx into n. Similarly, Sy is equal to, this is the total stress. Sorry, this is the total force. This is the equation of total force, not the stress. Total force. Total force in x, y, and z directions. In z direction. Okay. Total force in x, y, and then z directions. So Sy is equal to your tau is tau xy into L plus sigma y into m plus tau zy into n. Similarly, you can say, right, sigma z is equal to tau xz L plus tau tau zy L plus sigma z into n. This is the total force. Force means that in the stress there is area is multiplied. In everywhere area is multiplied. As we are taking the area is everywhere multiplied, so it will be cancelled. So we are not writing A here. The I think you will understand this equation, the total force. This is not the stress. As you know that the Sx, Sy and Sz are the component of the stresses, total stress S. Sx, Sy, Sz are the component of the total stress S. So this is here. If you go for the total force in any direction, as we know, force is equal to stress into area. We know force is equal to stress into area. So this is the case of force. This is all other forces. Means force in x direction, total force in x direction. So total force in x direction, we are writing Sx into A equals to your sigma x AL. This is the area. Similarly, we are writing tau yx am plus tau zx an. So everywhere we are cancelling a. Now we have the equation like this. Similarly, for all directions, y and z directions also, we are calculating the stresses. There are two equations we are proved there. This is equation 3. This is equation 4. This is equation 5. 3, 4, 5. So, so our purpose is to find the normal stress sigma. Main purpose. What is that purpose? We will be proposed to find the normal stress sigma, to find a normal stress sigma and shear stress on the oblique plane. Our purpose is to find out these two cases. So it is necessary to determine the components of Sx, Syz in the direction of the normal and of the plane. Thus, so we can write down in terms of that we are saying that there are two equations we are writing. The first equation S is equal to S square is equal to sigma square plus tau square. We are writing this. So that is essential to write the sigma in terms of Sx, Sy and Sz, because the S has three components. S are these three components. So those S are these three components. The total stress S has three components, Sx, Sy, Z. So it is essential for us to write down the total stress in that format. So we can write this format in the form of the cosine components. So we will write the total stress sigma in the format of cosines. So we know the total stress is sum of the stresses. So total. If you go here, similarly, if you go here to calculate the total stress, nothing. The Sx, the cosine angle between the quiescent SXL. Now this is SYM. Now SZN. This is the total stress sigma. The total stress sigma. After substituting equation 17, if you putting the, as we know the Sx values, before in that equation we are find the each values Sx, we are find the Sy values, we are find the Sz values. Now we put the now if we put the values of Sx, Sy and Sz in this equation, then we will find a complete equation of this. Now put these values, put the values of Sx, Sy, like that is equation 3, 4, 5. Put the values of equation 3, 4, 5 in this equation. This is equation number 6. I will make it the equation number 6. Put the values of equation 3, 4, 5 in equation 6. If you putting the values, we'll find that sigma is equal to there is a sigma x L square plus sigma y m square plus sigma z n square plus 2 tau xy lm plus 2 tau yz mn plus 2 tau zx zn sorry zx n. This is the equation number 7. After putting the values of Sx, Sy and Sz in equation number 6. So here we will go for the assumptions that what will go here, the tau xy equals to tau yx. Similarly, tau zx is equal to tau zy. zy. By this putting this assumptions, we will find this is our complete equation in terms of your sigma x, sigma y, and sigma z. Okay, as you find the values of Hx and Sy and Hz, this is now a new equations where now we see here what we are now values of we are now this is our equation. This equation is our equation number 1. See this is our equation number 1. In this equation, previously in equation 2, we are find the values of S here, is there. Now in equation 7, in equation 2, we are find the values of these two. So in equation number 7, we are find the, now in equation number 7, so just, so in now here we are equation 2 we are find the values of total stresses. In equation 7 also we are find the values of this in equation 7 also. So now we are writing this in that format that equation 7 we are proved in equation 7. Now this is as the initial equation is that we have that initial equation a square is equal to sigma square plus tau square. Now we got both the values of a square and sigma square. So tau square can be easily calculated. Tau square can be easily calculated by this writing this equation in that format. Writing in that format also. Tau square is a square minus sigma square. Now in that format we can calculate the values. In that format we can now calculate the values. So if you put the values there now, then we will go for easily the calculations. Now put the values. Now put the values and we will get the values of shear stress. To get the magnitude now we have the initially we have two things to calculate. The first thing is that to calculate the sigma and then tau. Now in these two equations we are calculated the values of sigma and values of tau. So what to do? So, though the magnitude is calculation, both the values are calculation. That means the magnitude is calculated. The magnitude is calculated, but we don't have till now. We don't know the directions. We don't know the directions. Till now, we don't have the directions of both the sigma and the total stress, is normal stress and the shear stress. So it is necessary to calculate the directions of the component, direction of the shear components and the normal stress components. So to calculate the directions, it is necessary to resolve the stress components. The stress components means Sx, Sy, and Sz. It is necessary for the resolve the stress component in y and y dash and z dash directions. In y dash and z dash directions in the oblique plane. In the oblique plane, we are taking that oblique plane. In the oblique plane, if we making two directions of y dash and z dash, the new directions, new oblique plane directions. So in that case, we will resolve the stress components Sx, Sy, and Sz in y dash direction and z dash directions. This development will not be carried out here because the prominent equations can be derived more easily. So the plastic flow, generally the plastic flow involves shear stresses. we are reading about the plastic stresses. The plastic flow stresses, shear stresses. Shear stress is very much important for plastic flow. Shear stress is very much important for plastic flow. Plastic flow is generally involved for the shear stresses. So it is important to identify the planes on which maximum or principal stresses occur. So it is very much important to identify the maximum or principal stresses occur. So in two-dimensional cases, last we have during the discussions we are what we do that we are calculating for the two-dimensional stresses. Previously we are already calculated the two-dimensional stress case. So we are already go for the two-dimensional the maximum shear stress for in a two-dimensional case. We are already go for that. Tau max we are calculated in two-dimensional case. I think you will remember this. We are already calculated tau max in two-dimensional case. So similarly, so what is that value of tau max in two-dimensional case? This is just the mid of the two stresses, sigma 1 plus sigma 2 by 2 in two-dimensional case. But in three-dimensional case, that cannot be happen there. It will be some different that. Uh, and plane half is that we have that tau max will be on the half between the two principal planes. Therefore, it is easiest to define the principal shear plane in the terms of three principal axes 1, 2, 3. So tau square will be as we have writing this equation here. We are writing that tau square is equals to your a square minus sigma square. We are here in three-dimensional case. We are writing in that format. In three-dimensional case. So put the values by putting the values here now, we'll go for the calculations. So write the tau square. The tau square will go for the equations for the tau square. Tau square is written as by putting the values of sigma 1 minus sigma 2 square L square M square plus sigma 1 minus sigma 3 rho square sigma 1 and sigma 3. Sigma 1 and sigma 3 means here we will multiply here L square and N square. Remember this terms. It is a LM where to put the elements. If you find the components like 1, that means here the cosine angle will be L. If there is a component 2, then cosine angle will be M. Similarly, if there is a term sigma 3, then means there is a cosine angle of N. Similarly, we can put the again we can write this equation like that: sigma 2 minus sigma 3 square, that is M square minus N square, M square N square. Now this is another equation. We are going for the equation number 8. This is equation number 8. From this equation, we are calculating where we get the value. See this. There is a two stress components. One is S and is sigma. But we have the cosine components. We are go for the two directions, y dash and z dash directions. So another z direction. That means we are resolving the stresses in particular directions. By resolving, what happens during the resolution, there is a cosine angle. So this is the L and M are comes due to the cosine angles. If there is a single stress component, we can write sigma tau square is equal to sigma 1 square minus sigma 2 square. But if there is three-dimensional cases, that's why we are writing here sigma 1 minus sigma 2, then the cosine components Lm. Similarly, there is another stress, another direction, that is another plane, that is sigma 1, sigma 3 plane. So here L and N. Similarly, there are 2 and 3 planes, then we will have stress on the y, x and z is this is y and z plane. This is x and y plane. The stress on the x and y plane. This is the stress on the x and z plane, and this is the stress on the y and z plane. So this is our equation number 3. If you calculate where LMN, as we know, the LMN are the direction cosines between the normal and the oblique planes. The principal shear stresses occur in the following combination of direction cosines that bisect the angle between the two principal stresses. So in similar way, we'll go for the determinant form. We'll see what will happen there. If you're writing this equation in the format, this is our equation. This is our equation. So we'll write this equation in the format. See, L, M, and N here. L, M, N here. If you put L is equal to 0, cosine angle first 0, then this is plus or minus 1 by 2 the root over. This is plus or minus by 2 the root over. Then what will be the shear stress? The question is what will be the shear stress? If we have these type of values, L is 0, M is 1 by root 2 and N is 1 by root 2, then I put these values. Now put these values, L is equal in equation 8, L is equal to 0. That means this term will be total, this term will be 0. Again, where L is 0, L component there, the total term will be going to 0. This component will also going to be 0. So we have only, if you're going for the calculation of the shear stresses, so we have only, and putting the values of M and N here. Put the values of M and N here, we'll find that tau here is, this is tau. So tau 1 is equal to what? Tau 1 is equal to sigma 2 minus sigma 3, sigma 2 minus sigma 3 by 2. Similarly, put the values and reverse the values. So cosine angle means cos angle, cos will be 0 maximum, cos will be minimum 0, that will maximum, we can put the maximum because there is the value cannot be matched with M and N. So that's why this is the optimized condition we are putting here. Similarly, we can go for here writing that L is plus or minus 1 by root 2. Then M is equal to 0 and N is plus or minus 1 by root 2. So what will go 1 by root 2. So what we will find here? So what we'll find? We'll find the tau 2. We're writing this tau 2. Tau 2 is that the where there is M component, that component will also 0. This component will going to be 0. See, and where is another M? This component will be going to 0. So now this component will be present, that is sigma 1 minus sigma 3 divided by 2. Sigma 1 minus sigma 3 divided by 2. Next we'll see here by putting the equations. See, now we'll put this L is plus or minus 1 by root 2. Sorry, root 2, whole root 2, not root 2. And this is also M is 1 by root 2, then N is 0. If you put in that way, so we'll find that tau 3. We'll find the tau 3. Tau 3 will be, that is sigma 2, sigma 3, sigma 1, sigma 3. Sigma 1 minus sigma 2. Sigma 1 minus sigma 2 by 2. Sigma 1 minus sigma 2 is 2 by 2. So in that format, in that way, we'll find the value. See here, we will find the three values of, shear stress. One is tau 1, another is tau 2, and there is tau 3. In that case, in three-dimensional cases, we'll find the three values of shear stress, that is tau 1, tau 2, tau 3. From here, from these equations, by seeing these equations, you can easily now tell that which one is the maximum shear stress and which one is the minimum shear stress. How can you tell that? Who can you tell that which one is maximum shear stress? Which one is maximum shear stress? Which one is maximum stresses and which one is minimum shear stress? So see this, I am again writing this equation. Tau 1 is, what is the value of tau 1? Now sigma 2 minus sigma 3 by 2. Tau 2 is sigma 1 minus sigma 3. Sigma 1 minus sigma 3 by 2. And another tau 3 is sigma 1 minus 2 by 2. So here, which one by mathematically you say which one it will be maximum? As we know that what we know, the sigma 1 is the maximum. Sigma 1 is maximum always, and sigma 3 is minimum always. Minimum always, and sigma 2 is in between these two, in 2. So if you see mathematically which one is maximum, you can tell me. Where the difference is higher, that will be the maximum. If the difference is between maximum and minimum, if there is a stress difference between maximum and minimum, then that will be the maximum value. So we can easily say that this will be our tau max. You can easily say this one will be our tau max, because the difference is tau sigma 1 minus sigma 3. Sigma 1 is maximum, sigma 3 is minimum. So the upper part will be maximum. That means it will be the maximum value. So we can easily say here that tau 2 is our maximum shear stress. Tau 2 is our maximum shear stress. So we'll write that tau 2 is equal to tau max. Tau max, that is sigma 1 minus sigma 3 by 2. Sigma 1 minus sigma 3 by 2. So similarly, the minimum we can say the minimum, which one is minimum? Minimum shear stress, that is the difference is higher. Difference is higher means sigma 2 minus sigma 3. Sorry, low difference, sigma 2 minus sigma 3. That will be. So in that format, we will go for the calculation of the maximum values and the minimum values of the shear stress. The maximum shear stress is important in theories of where it will be important. Now it will be important in theories of yielding. Theories of yielding. Theories of yielding. It will be very much important in the theories of yielding and also the metal forming, as we are going to read the metal forming. Metal forming in yielding and metal forming operations. So this is all about the stresses on a plane, on an oblique plane. The stresses means the shear stress and the shear stress and also the principal stress sigma. Okay, the normal stress sigma. So so another thing is that you to how to represent these principal planes, principal directions. So the principal shear stresses for a cube whose faces are principal planes. For each pair of principal stresses, there are two planes of shear stress. For each plane of each pair of principal stress, there are two planes of principal shear stresses. Remember this. For each pair of principal stresses, there are two planes of principal shear stress, which bisects the direction of the principal stresses. That is always the bisects of the principal stresses. I am showing you one. I'm just showing you one. See this. So I will show you one. This is one principal direction. Okay. This is I'll make it to show you. Touching it, the plane.